That star should not be there. Look up at the night sky. Pick any star, any one of the 400 billion in our galaxy alone. Now I'm going to tell you something that should keep you awake at night. That star should not be there. None of them should be there. According to the laws of physics, the very same laws that I spent my life working on the universe should be an infinite, cold, perfectly dark, perfectly empty void. No stars, no galaxies, no planets, no oceans, no you. The universe started with a big bang. Fine. But here's what the equations say should have happened next. Nothing. An evenly spread cloud of hydrogen gas, cooling, expanding, thinning forever. No clumping, no collapsing, no igniting. Just darkness. Just silence. Just the most boring cosmos you could possibly imagine. Every single star in the sky exists because of a set of cosmic accidents, improbabilities stacked on improbabilities, so extreme that the word lucky becomes almost laughable. The universe had to lie to the laws of physics in at least 4 completely separate ways just to get the lights on. I want to show you every single one of those lies. Because the real question, the one that has been haunting physics for decades, is not how the stars formed. It's why anything is here at all. The annihilation that should have ended everything. Let me start at the very beginning. Not the beginning in the vague poetic sense, but the actual beginning, the first fraction of a second after the Big Bang, because this is where the first catastrophe should have happened, and where the universe performed its first impossible trick. The Big Bang did not create matter. That is not what the Big Bang did. What the Big Bang created in the first moments was energy pure, concentrated electromagnetic energy in the form of photons, gamma rays, the most intense radiation you can possibly imagine. And as that radiation cooled and expanded, it did what radiation does when it cools. It converted into particles. Here is the critical thing. When energy converts into matter, this is standard, well-tested, experimentally confirmed quantum field theory. It always creates matter and antimatter in exactly equal amounts. Always. Without exception. Every time you create a proton, you create an antiproton. Every time you create an electron, you create a positron. The law is absolute. Matter and antimatter are born in pairs, equal numbers, every single time. So the Big Bang should have created equal amounts of matter and antimatter. And when matter meets antimatter, what happens? Annihilation. They destroy each other completely, converting back into pure energy, into photons. 1 proton plus 1 antiproton equals 2 gamma rays. That's it. Gone. No proton left over, no antiproton left over, just light. And here is what this means for our universe. If the Big Bang created equal amounts of matter and antimatter, every single particle of matter would have found its antimatter partner and annihilated. Every proton would have met an antiproton. Every electron would have met a positron. The entire content of the universe, all the matter from which all the stars and galaxies would eventually form, should have been annihilated in the first seconds. The universe should have ended as nothing but a bath of photons, cooling and expanding into infinite darkness. There should be no matter, no atoms, no hydrogen, no stars, no us. And yet here we are. Here are the stars. Here is the matter. Here you are, sitting wherever you are, made of atoms, which are made of protons and electrons, which by all rights should not exist. The 1 in a billion miracle. Baryon asymmetry. This problem has a name. Physicists call it the baryon asymmetry, the mysterious, completely unexplained excess of matter over antimatter in the observable universe. And when we actually calculate how big this excess is, the numbers become extraordinary. For every billion antiprotons produced in the Big Bang, there were approximately 1,000,000,001 protons. That's the asymmetry. 1 extra proton for every billion annihilations. Everything you see in the universe, every star, every galaxy, every planet, every atom in your body is the leftover residue of that 1 in a billion excess. All the rest annihilated. You are literally the debris. Now, the particle physicists will tell you, and they are right, that this asymmetry is required by something called the Sakharov conditions, after the Soviet physicist Andrei Sakharov, who worked out in 1967 what physical processes are needed to generate a matter-antimatter asymmetry. You need 3 things: baryon number violation, CP violation, and departure from thermal equilibrium. And we know that the universe satisfies all 3 conditions in principle. The standard model of particle physics has CP violation built into it. But here is the problem, and it is a serious one. When you calculate how much matter-antimatter asymmetry the Standard Model actually predicts, when you do the honest calculation, you get a number that is about 10 billion times too small. The CP violation in the Standard Model is real, but it is nowhere near large enough to explain the asymmetry we actually observe, which means we are missing something. There is physics beyond the Standard Model, some mechanism we do not yet understand, that generated the matter-antimatter asymmetry. We have experimental hints, neutrino masses and mixing angles that suggest new physics, possible new sources of CP violation, extensions of the Standard Model like supersymmetry or leptogenesis, but we do not have the answer. And this is not a minor technical detail. This is perhaps the most profound question in all of physics. Why is there something rather than nothing? Why did the universe produce even that 1 in a billion excess of matter? If the symmetry had been exact, as the simplest version of quantum field theory demands, there would be nothing. Absolute nothing. Not empty space, not dark matter, not radiation, just photons cooling forever. The existence of every atom in the universe depends on a mechanism we do not understand. There are experiments running right now at facilities around the world, searching for new sources of CP violation, searching for evidence of leptogenesis, measuring the properties of neutrinos with exquisite precision, T2K in Japan, NOVA in the United States. The Deep Underground Neutrino Experiment just beginning to take data. These are humanity's attempt to answer the question of why there is something rather than nothing. And until we find the answer, the existence of every star in the sky rests on an unexplained miracle. The universe should have been empty. It isn't. And we don't fully know why. The perfectly smooth universe, no stars allowed. All right, suppose I grant you the first miracle. Suppose something, some mechanism we don't yet understand did create that 1 in a billion excess of matter. You've got your protons and electrons. The universe is now a vast, hot, dense plasma of hydrogen and helium, expanding and cooling after the Big Bang. Does this give you stars? No, absolutely not. Not automatically. Not from the simple existence of matter. The existence of hydrogen is necessary, but nowhere near sufficient. What you need is for that hydrogen to clump, to concentrate, to collapse under gravity into regions dense enough and hot enough to ignite nuclear fusion. And here is where the second disaster should have happened. The early universe was almost perfectly uniform. This is not a speculation. It is one of the most precisely measured facts in all of cosmology, confirmed by the cosmic microwave background radiation, the afterglow of the Big Bang that we can still observe in extraordinary detail today. The temperature of the early universe varied by only about 1 part in 100,000 from place to place. The density varied by equally tiny amounts. The universe was, to an extraordinary precision, smooth. And smooth means no stars. Let me explain why. For a cloud of gas to collapse into a star, gravity has to win a competition against pressure. The gas is hot. Hot gas has pressure. Pressure resists compression. If the gas is distributed perfectly uniformly with no density fluctuations, there is nothing for gravity to grab onto. The gravitational pull from every direction is balanced by an equal pull from the opposite direction. The gas doesn't collapse. It just sits there, expanding with the universe, getting thinner and cooler forever. This is not a new insight. It was worked out rigorously by the British physicist James Jeans in the early 20th century. The Jeans instability tells us the minimum mass and size that a gas cloud must have for gravity to overcome pressure and cause collapse. And it tells us something important. Tiny density fluctuations lead to tiny gravitational instabilities, and tiny instabilities grow slowly, very slowly. Here's the thing about the cosmic density fluctuations. They were not just small, they were almost exactly the right size to give us the universe we observe. 1 part in 100,000, not 1 part in a million that would produce too few structures. The fluctuations would take too long to grow. The universe would be empty. Not 1 part in 10,000 that would produce too many structures. Everything would collapse too fast into supermassive black holes. Stable stars and galaxies would never form. 1 part in 100,000 to within a factor of a few. Why? Why were the fluctuations that size? That is the question. Inflation, the CMB, and the dark matter scaffolding. The answer involves one of the most remarkable, and I have to be candid, speculative ideas in modern cosmology: inflation. The theory of cosmic inflation, developed principally by Alan Guth in 1980 and extended by Andrei Linde and others, proposes that the very early universe underwent a period of exponential expansion, expanding by a factor of at least 10 26 inches, a tiny fraction of a second. During this inflation, quantum fluctuations, the inherent randomness of quantum mechanics at the smallest scales, were stretched to macroscopic sizes, imprinting density variations on the universe that would eventually seed the formation of all structure. Let me dwell on this for a moment, because I think it is one of the most extraordinary ideas in the history of science. The seeds of every galaxy, every star, every planet, every living thing in the universe were quantum fluctuations, the inherent probabilistic fuzziness of quantum mechanics that were magnified to cosmic scales by a period of explosive expansion in the first 10 negative 32 seconds of time. The quantum foam of empty space became the large-scale structure of the universe. This is testable, and it has been tested. The Planck satellite, the WMAP satellite before it, have mapped the cosmic microwave background with extraordinary precision, measuring the spectrum of those density fluctuations, their amplitude as a function of angular scale, and comparing it to the predictions of inflationary models. The agreement is remarkable, but we do not have a confirmed, complete theory of inflation. We don't know the specific model of inflation, what drove it, or whether it is part of a larger multiverse picture. And even granting the fluctuations there is still the problem of how the fluctuations grow into stars. And in a universe of ordinary matter alone, the growth is agonizingly slow. Calculations show that the first stars would have taken billions of years longer than they actually did. Something accelerated the process. Something gave gravity additional scaffolding to work with. And that something is dark matter, the mysterious, invisible, non-interacting substance that makes up about 27% of the energy content of the universe and interacts with ordinary matter only through gravity. Dark matter, indifferent to radiation, started building up gravitational wells billions of years earlier. And when ordinary matter was finally free to respond to gravity, it fell into those pre-built dark matter wells, accelerating the formation of galaxies and stars by hundreds of millions of years. Without dark matter, the first stars would have formed much later, if at all, and we don't know what dark matter is. The gravitational evidence is overwhelming, from galaxy rotation curves to gravitational lensing to the CMB power spectrum, but we do not know its particle physics nature. So to summarize where we are, stars require matter, unexplained asymmetry, density fluctuations, inflation, mechanism unclear, and dark matter, unknown. We're 3 unexplained miracles in, and we haven't even gotten to the stars themselves yet. Fine-tuning the proton-neutron mass conspiracy. Let's say we've gotten past the first 2 miracles. We have matter, we have density fluctuations, we have dark matter providing gravitational scaffolding. The first clouds of hydrogen gas are beginning to collapse. Finally, we're going to get a star. Not so fast. For a collapsing cloud of gas to become a star, rather than just a big, dark, cold ball of compressed hydrogen that never ignites the temperature at its center, has to reach about 10 million degrees Kelvin. At that temperature, protons are moving fast enough that the quantum tunneling effect allows them to overcome the electromagnetic repulsion between them and get close enough for the strong nuclear force to grab hold and fuse them together. Hydrogenfusion, the release of nuclear energy, the birth of a star. But fusion requires the right balance between the fundamental forces of nature. And here is where we encounter what I believe is one of the most unsettling facts in all of physics. These constants are extraordinarily finely tuned. Let me give you a specific example that I find particularly striking. The proton and the neutron have almost identical masses. The proton mass is 938.272 MeV. The neutron mass is 939.565 MeV. The neutron is heavier than the proton by about 1.293 MeV, roughly 0.14%. This seems like a trivial detail. It is not. This small mass difference has enormous consequences for the existence of stars. First, consider hydrogen. A hydrogen nucleus is a single proton. A helium-4 nucleus consists of 2 protons and 2 neutrons. For helium to exist, neutrons must be stable inside atomic nuclei. And neutrons are stable inside nuclei because the energy gained from the strong nuclear force overcomes the mass difference. But this only works because the mass difference is small. If the neutron were much heavier relative to the proton, say if the mass difference were not 1.293 MeV but 3 or 4 MeV, neutrons would not be stable inside nuclei. Helium would not exist, and all nuclear chemistry beyond hydrogen would be impossible. No carbon, no oxygen, no us. Conversely, if the neutron were lighter than or equal to the proton, then the free neutron would be stable, and all the neutrons produced in the Big Bang would still be around today. The universe would have a very different chemical composition, probably mostly neutrons, which would not combine into the light atoms we need for chemistry. The proton-neutron mass difference is set by the difference between the up quark mass and the down quark mass, which in turn is set by the details of how the Higgs field couples to these quarks. Those parameters appear to be tuned, at the level we currently understand them, to a value that allows both hydrogen to be the primary constituent of the universe and helium, 4 to be stable. One small number, 2 simultaneous requirements. And it works. Fred Hoyle's prediction and the carbon resonance. But the most famous example of fine-tuning in nuclear physics, the one that, when I first encountered it, genuinely gave me a feeling of vertigo, is the carbon resonance. This was predicted by the British astrophysicist Fred Hoyle in 1953, before it was experimentally confirmed. And the story of how Hoyle predicted it is one of the most extraordinary episodes in the history of science. Hoyle was thinking about where the carbon in the universe comes from. Carbon is the 4th most abundant element in the universe and the basis of all organic chemistry. It is made in the cores of stars through a process called the triple alpha process. 3 helium nuclei, alpha particles, fused together to form a carbon, 1,2 nucleus. This process has to occur in 2 steps because the probability of 3 particles colliding simultaneously is essentially 0. First, 2 helium, 4 nuclei fuse to form beryllium, 8. Then, beryllium, 8 captures a 3rd helium, 4 to form carbon, 1, 2. But there's a problem. Beryllium, 8 is unstable. It decays back into 2 helium, 4 nuclei with a half-life of about 10, -16 seconds. So the window for a 3rd helium nucleus to arrive and fuse is extraordinarily small. Hoyle realized that this process could only work if there was a resonance in carbon 1, 2 at exactly the right energy, a resonance that would dramatically enhance the probability of the beryllium, 8 capturing a helium, 4 before it decays. Without this resonance, the triple alpha process would be too slow to produce significant amounts of carbon, even in the cores of massive stars over billions of years. The universe would have almost no carbon, and Hoyle, reasoning backward from the existence of carbon, and therefore of life, predicted that such a resonance must exist. He predicted its energy, approximately 7.65 MeV above the ground state of carbon, 1, 2. He presented this prediction to nuclear physicists at Caltech, who were initially skeptical but agreed to look for it experimentally. They found it at exactly 7.65 MeV, just where Hoyle said it had to be. The carbon resonance at 7.65 MeV, the Hoyle state, is one of the most precisely tuned numbers in nuclear physics. Calculations using lattice quantum chromodynamics show that if the light quark masses were changed by even a few percent, the Hoyle state would move to the wrong energy, and carbon synthesis in stars would be dramatically suppressed. A few percent change in the quark masses out of a universe where these masses could in principle be anything would mean no carbon-based life, no observers. There's more. Just above the carbon, 1,2 Hoyle state in the oxygen, 1,6 nucleus, there is an anti-resonance, a state that if it was slightly lower in energy would allow carbon 1,2 to capture another helium 4 and become oxygen 1,6 far too efficiently, depleting all the carbon. The carbon and oxygen resonances have to be tuned in opposite directions simultaneously to give the universe its measured carbon to oxygen ratio. The fine-tuning is real. The calculations are solid. The universe appears tuned for stars, and we don't know why. The sun burns slower than your body, here's why. I've told you about the matter-antimatter asymmetry that gave us any matter at all. I've told you about the density fluctuations in dark matter that allowed that matter to collapse into the first clouds. I've told you about the extraordinary fine-tuning of nuclear physics that allows hydrogen to fuse into helium and helium to fuse into carbon. Now I want to talk about the energy that keeps the stars burning and why, by every right, they should have burned out billions of years ago. Stars live on nuclear fusion. The sun fuses about 600 million tons of hydrogen into helium every single second. It has been doing this for about 4.5 billion years. It will continue for another 5 billion years. The total energy released in this time is almost incomprehensibly large, about 1044 joules over its entire lifetime. But here's the thing. The rate at which hydrogen burns in the sun is extraordinarily slow. Far, far slower than you might expect. In the sun's core, at a temperature of 15 million degrees and a density of 150 grams per cubic centimeter, a proton has to wait, on average, about 5 billion years before fusing with another proton. 5 billion years. The reaction rate is so slow that the power output per cubic meter of the sun's core is actually less than the power output per cubic meter of a human body, about 276 watts per cubic meter in the solar core, compared to about 1,000 watts per cubic meter for human metabolism. The sun is not burning hot and fast. It is burning at a barely there trickle, sustained over billions of years. And it is this slow burn that makes it possible for planets to remain habitable for the billions of years needed for complex life to evolve. Why is the reaction so slow? Because the first step of hydrogen fusion, the proton-proton chain, involves a process that is almost impossibly improbable. Two protons collide. They have to stay together long enough for one of them to undergo a process called inverse beta decay to be converted into a neutron by the weak nuclear force, emitting a positron and a neutrino. This is a weak interaction. And weak interactions are, as their name implies, extremely weak and slow. The proton-proton fusion rate depends on the strength of the weak nuclear force. If the weak force was slightly stronger, the proton-proton chain would proceed faster. Stars would burn through their fuel more quickly, and there might not be enough time for complex life to evolve. If the weak force were weaker, the initial moments of the Big Bang would have proceeded differently. Neutrinos would have decoupled from matter at different times. The helium abundance from Big Bang nucleosynthesis would be different, and the chemical evolution of the universe would have unfolded differently. The sun's lifetime, about 10 billion years, is long enough to allow the evolution of complex life on Earth, which required roughly 4 billion years from the origin of life to the emergence of technological intelligence. One constant, one value. The difference between a dead cosmos and a living one, supernovae, neutrinos, and the birth of heavy elements. But the connection between the weak nuclear force and the existence of stars goes even deeper, in a way I find especially beautiful. After a massive star, much more massive than the sun exhausts its nuclear fuel, the core collapses. The collapse is catastrophic and rapid. The core goes from roughly the size of the Earth to roughly the size of a city, about 10 kilometers in radius, in less than a second. The density exceeds 14 grams per cubic centimeter. And then a supernova happens. Or does it? For a long time, this was actually a serious problem in astrophysics. When we ran the computer simulations of core collapse, the supernova didn't explode. The shock wave formed when the collapsing core bounced, but within milliseconds, the shock wave stalled. It lost energy as it propagated outward through the infalling material and simply stopped. The star didn't explode. It just continued to collapse into a black hole in the simulations. The missing ingredient was neutrinos. The collapsing core produces an incredible flux of neutrinos, about 1058 neutrinos in a few seconds, carrying 99% of the gravitational energy released in the collapse. These neutrinos stream outward through the stalled shock wave. And even though neutrinos interact very weakly with matter, the density of the shock wave is so extreme that even the tiny interaction probability translates into significant energy deposition. The supernova explosion is powered by neutrino energy. Neutrinos particles so weakly interacting that a light year of lead wouldn't stop. Most of them are what drive stellar explosions. And those explosions are what scatter the heavy elements, carbon, oxygen, silicon, iron, all the elements heavier than helium into the interstellar medium, where they become available for incorporation into new stars, planets, and eventually life. Here is the key point. The entire cycle of stellar evolution, heavy element production, and chemical enrichment of the universe depends on the weak nuclear force being exactly the strength it is. Too strong. Stars burn too fast. No time for life. Too weak. Supernovae don't explode. Heavy elements stay trapped in stellar remnants. The universe remains chemically primitive. And this is one of the most mind-bending aspects of the physics of stars. The same constant, the weak interaction coupling strength that determines how slowly hydrogen fuses in the sun, also determines how violently supernovae explode. It has to be tuned in both directions simultaneously. slow enough burning for long-lived stable stars, energetic enough neutrino interactions for supernova explosions. One number, two contradictory demands, one solution. The universe didn't just produce stars, it produced the right kind of stars in the right abundance with the right lifetimes. And at every step, the physics had to be just right. The cosmological constant, 10 to the power of 120 against the odds. I've been building a case that the existence of stars requires a set of extraordinarily specific physical conditions. Let me now talk about perhaps the most extreme example of fine-tuning in all of cosmology. So extreme that when I first learned the numbers, I had to sit quietly for a while and think about what they actually meant. The problem is called the cosmological constant, or equivalently, dark energy. In 1917, Einstein introduced the cosmological constant into his equations of general relativity as a term that represented the energy density of empty space, what he called the vacuum energy. He introduced it to make a static universe possible, then abandoned it when Hubble discovered that the universe is expanding. Einstein called it his greatest blunder. But the cosmological constant came back with a vengeance in 1998 when two independent teams of astronomers, one led by Saul Perlmutter, one led by Brian Schmidt and Adam Rees, measured the distances to distant type Ia supernovae and found that the expansion of the universe is accelerating. Something is pushing the universe apart, accelerating its expansion against the pull of gravity. That something is the cosmological constant, or dark energy. It amounts to about 68% of the total energy content of the universe. Now here is where things get deeply disturbing. In quantum field theory, the framework that underlies our best theory of all the fundamental forces, the vacuum is not empty. The vacuum is seething with quantum fluctuations, virtual particles constantly appearing and disappearing on timescales governed by the Heisenberg uncertainty principle. And these quantum vacuum fluctuations contribute to the energy density of space. When you calculate the vacuum energy density from quantum field theory, you get a number. It is not a small number. The vacuum energy density from quantum field theory, calculated using the standard model of particle physics up to the energy scales we have probed with particle accelerators, is approximately 110 joules per cubic meter. The observed cosmological constant, the dark energy density that causes the universe's expansion to accelerate, corresponds to an energy density of approximately negative 10 joules per cubic meter. The ratio between the predicted vacuum energy and the observed dark energy density is 120, one followed by 120 zeros. The discrepancy between theory and observation is a factor of 120. This is the largest discrepancy between theory and experiment in the history of science. By an enormous margin, every other successful physical theory agrees with experiment to within factors of 2 or 3, or a few decimal places, or at worst a few orders of magnitude. The cosmological constant problem is a discrepancy of 120 orders of magnitude. What this means is that something, some mechanism, some cancellation, some physics we don't understand is suppressing the vacuum energy by a factor of 120 from its natural value, not exactly 0, to an incredibly small but non-zero positive value. And this value has to be in a very specific range for the universe to contain stars. Cosmological calculations show that if the cosmological constant were as large as the naive quantum field theory calculation suggests 120 times larger than it is, the universe would have undergone runaway expansion in the first fraction of a second, and no gravitationally bound structures of any kind would have formed. The universe would be an infinite, diffuse, rapidly expanding sea of unclustered particles. No galaxies, no stars, nothing. On the other side, if the cosmological constant were strongly negative, the universe would have collapsed back on itself in a big crunch long before stars had time to form. The probability that the cosmological constant would randomly take a value in this narrow window is roughly 1 × 120. This is not a number that comes from any known symmetry or dynamical mechanism. We genuinely do not understand why the cosmological constant is what it is, and on its precise value rests the existence of everything. Anthropic principle, multiverse and string theory. We've traveled a long way together. Let me bring everything together and then push to the deepest question, because the question of why the universe has stars opens up into something that I think is more profound than the existence of stars themselves. To have stars The universe needed, at minimum, a matter-antimatter asymmetry of 1 part in a billion, generated by a mechanism we don't understand. Density fluctuations of approximately 1 part in 100,000, likely generated by inflation, mechanism uncertain. Dark matter of unknown composition, providing gravitational scaffolding for structure formation. A nuclear physics finely tuned to allow hydrogen fusion and carbon synthesis. A cosmological constant suppressed by a factor of 10, 120 from its natural value. A weak nuclear force of precisely the right strength to allow both stable, long-lived stars and supernova explosions. Each of these is, on its own, an unsolved problem in fundamental physics. Together, they constitute the existence problem. Why does the universe have the specific properties needed for complex structures to exist? Now, I've seen how physicists react to questions like this. Some get uncomfortable and change the subject. Physics, they say, is about measuring and predicting, not about why the constants have the values they do. Others invoke the anthropic principle. We observe the constants to have the values that allow our existence, because if they had different values, we wouldn't be here to observe anything. Others hope for a theory of everything that will derive the constants from first principles. The anthropic principle is more subtle than it first appears. In its most rigorous form, the statement that observers can only arise in universes that permit the existence of observers, it is obviously true. The question is whether it is informative. If there is only one universe, then the anthropic principle just restates the observation that we exist in conditions compatible with our existence, which tells us nothing about why those conditions hold. But if there is a multiverse, a vast ensemble of universes with different physical constants, then the anthropic principle becomes a genuine selection effect. Of course, we find ourselves in a region of the multiverse that permits our existence because only those regions have observers. The multiverse is not a comfortable idea. It is not falsifiable in the traditional sense. But inflationary models that predict a multiverse also make predictions about the statistics of the CMB that can be tested. The string theory landscape makes predictions about the distribution of constants that can be compared to what we observe. These are indirect tests, but they are tests. And physics has repeatedly expanded its picture of the world to include things we cannot directly observe. Atoms were once unobservable. Electrons were theoretical entities before there was direct evidence. Quantum fields extend throughout space in a way that is not directly perceptible. If a multiverse is the correct explanation for the fine-tuning, then the fact that we can't visit other universes is no more damning than the fact that we can't visit the interior of an electron. Why anything exists at all, the final question. The deepest response, the hope for a theory that derives the constants from first principles, is the one I find most appealing and also the most difficult. What would such a theory look like? It would be a theory so deep, so fundamental, that it did not have free parameters, a theory from which everything followed uniquely, including the values of the coupling constants and masses that appear as inputs in the standard model. It would be the complete, final theory of everything. We don't have such a theory. String theory is the best candidate, but it has the landscape problem. It seems to predict an astronomically large number of possible vacua with different physical constants, rather than a unique prediction. Loop quantum gravity is another approach, but it hasn't yet made contact with the standard model. What I believe, and this is my personal opinion, not physics, is that there is something deep we are missing about the relationship between mathematics and physical reality. The extraordinary fine-tuning of the constants suggests that the universe is, in some sense, more constrained than it appears that the constants are not arbitrary numbers but are determined by a structure we haven't found yet. But here is what I find most extraordinary, and what I want to leave you with. We human beings, made of atoms, living on a planet orbiting an unremarkable star in an ordinary galaxy, have managed to figure all of this out. We have measured the baryon asymmetry to parts per billion. We have mapped the cosmic microwave background to 1 part in a million. We have calculated the Hoyle state from first principles. We have measured the cosmological constant to a few % precision. We have built particle accelerators that probe the physics of the first trillionth of a second after the Big Bang. In less than a century of modern physics, we have gone from not knowing that the universe is expanding to knowing that its expansion is accelerating, that it is 13.8 billion years old, that it is 95% composed of dark matter and dark energy of unknown nature, and that the physical constants that govern its behavior appear tuned in multiple independent ways for the existence of complexity. And we are not done. We don't know why. Matter dominates antimatter. We don't know what dark matter is. We don't know what dark energy is. We don't know why the cosmological constant has the value it does. We don't know whether the universe is one or many. Every one of those open questions is a door. Behind each door is potentially a completely new kind of physics, new particles, new forces, new symmetries, new structures that we haven't imagined yet. The universe should not have stars. The physics says so. And yet look up. There they are. That is not a reason for mysticism. It is a reason for curiosity, rigorously pursued and never satisfied. I am a physicist. And the question I find most beautiful in all of science is the simplest one. Why is there something rather than nothing? We don't have the answer yet. But we are, for the first time in the history of life on this planet, asking it with equations and experiments and precision instruments pointed at the sky. And that is magnificent.